Let us imagine that we are looking at a star and we measure the wavelengths of some mission line and we find that they are varying. Something like this. Let's assume that the normal wavelength in the laboratory of this line is down here. Call it lambda naught. So what can we deduce from this? The first thing to notice is that the average wavelength is up here. So it's been shifted from lambda naught to a longer wavelength. That will be because the star is in a different orbit around the galaxy and moving away from us on average. So this doesn't tell us anything about any planets around the star, it just tells the relative velocity of that star and our own. We could look at that value here and convert that into a velocity of the star relative to the Sun using velocity over the speed of light equals the change in wavelength over lambda naught, the normal Doppler effect equation. So that tells us in this case the star is moving away from us. But what we're really interested in is the planet. So what we can see is a sinusoidal oscillation. What can we learn from that? And the first thing we can learn is the period here, p. That tells us how far away the planet that is causing this wobble is from the star, using the equation r equals the cube root g mass of the star times the period squared, convert that into seconds, if it's in some other units, over 4 pi squared. So we measure how long it takes, convert it into seconds, plug it in here. We have to know the mass of the star, which you can't derive from this data. You'd have to get that from modelling the spectrum of the colour of the star. That tells you how far out the planet is. If we then want to work out the mass of the planet, what we need to do is look at the shift here. We'll call that delta lambda. And this is going to be caused by the velocity of the star moving in its reflex motion. This wiggle is not the wiggle of the planet, it's the wiggle of the star caused by the planet. So if you look at, and it's off the average over here, not all the way down to lambda naught. So we can plug that into here to find out the velocity with which the star is moving in its reflex motion. So we know that the star is moving in a circle with velocity v. We don't know the radius of this circle. It's going to, we'll call it r star. It's going to be much smaller than the r we've worked out over here, which is how far the planet is from the star. But we do know the period it takes to go round. Now the period is just how long it takes to go all the way around, and so that's going to be the distance, which is going to be the circumference of that circle, which is just 2 pi r star, divided by the velocity. That equals the period. That's just definition. Distance divided by speed gives you how long it's going to take. So that means that r star, that is the reflex motion radius of the star, is going to be period times the velocity, which we've just measured using the Doppler effect from this, all over 2 pi. Once we know that, we can work out the mass of the planet if it's in an edge-on orbit, or more precisely, we can work out the mass times the sine of the inclination is going to be the mass of the star. That's the mass of the planet here. Mass of the star times r, that's how far out the orbit is from here, divided by r star, which comes from here and is the size of the reflex motion. This is only valid if r star is much less than r, but that's almost always the case for a planet orbiting a star. It wouldn't really work for a binary star. So that gives us the mass of the planet times the sine of the inclination, which is normally all we can ever work out.